Okay, today I'll be talking about knapsack problem. So basically, a knapsack problem is a optimization problem which is used to illustrate some problems and solutions. So it is derived using some constraint and the number of items that can be placed inside a fixed size of knapsack. So here the main element in knapsack is that we will be given some set of items with some specific weights, and their values will also their profit will also be given, and the number of items will be given. So the aim of this knapsack is to get as much as value into the knapsack. So knapsack is basically a container. We can also say it as a container or a bag in which we have to fill some items which have some specific weights. So the important thing and the aim is to get as much as value into the knapsack as possible, given with the weight constraint of the knapsack. So in knapsack problem, there is basically two versions of this problem. The first one is 0-1 knapsack problem, and the second one is fractional knapsack problem. So we can solve it using both of them. So here the items that are indivisible. So suppose items which are indivisible, you either take an item or not, is solved by dynamic programming. And the second one is that items that are divisible, you can take any fraction of that item using the greedy algorithm. So as we all know that lots of goods are transported daily from one place to another, and the problem over here is that the filling of the sack or we can also say a container. So the problem is that how we will fill that sack. The problem arises when the object is more and its weight is more and the capacity of bag is not that much. So it is where our problem arises. So if we will take, suppose we take a very less object, so that objects can be easily be fixed, put into the sack, then there is no problem. Suppose if I have to buy some potatoes. So we are buying 5 kg potato, 3 kg potato. So what we can do is that according to the capacity of the sack, we can reduce that the kg. Suppose we have 5 kg. So if the capacity is not much of the bag, we can take 2 kg or we can take 3 kg. So this means that it can be divided, it can be divisible. Suppose we are buying onion, potatoes, fruits, so we can reduce their quantity, we can divide them according to our quantity of the sack. So sometimes what happens is we are buying some mixer or fridge. These things cannot be divided, we cannot divide it, we cannot make it half. Let's take half, cut the fridge and take half. So at that time the items are indivisible, and during that time we either take an item or we do not take an item, and this is solved using dynamic programming. And in greedy algorithm, we can do is we can divide the uh, items. So here we can take any fraction of the item, and this is solved using greedy algorithm method. So let's first look at the greedy knapsack algorithm using greedy algorithm. So here I have taken one example over here. What I am doing over here is, okay, so here n, I have denoted n as number of the objects. So I am taking 7 object over here, and m is my capacity of the bag, which is 15. So I can fill 15. The capacity of my bag is 15. So over here I have made the table object for O and the profit. As we know, every object has its profits and weight. So my profit over here is P and weight over here is W. So here I have just arranged the table. These are my objects, 7 objects, and this is my profits for the 7 objects, and these are the weights of my object over here. So the basic objective over here in greedy algorithm is that we have to maximize the profit as much as possible, and the constraint over here is that we cannot take the objects more than the size of the capacity of the bag. So in this case, as we know, the capacity of our bag is only 15, so we cannot take anything more than 15. So over here my constraint will be the, that is total weight, that is summation of xi wi will be less than equal to 15. Either it will be 15 or it will be less than 15. So that is summation of xi wi is less than equal to m. That is the capacity of the bag over here. Also, the value of xi will be between 0 and 1. So in here, if we see in this case, we can fill our sack in any way. Either you can take objects whose weight are less, and or also you can take objects whose profit of weight is more. So in this case, if we see over here, the profit is 18 over here. The maximum profit is 18. The most profit is 18. So here what we are doing is that at first we are dividing our objects by profit by weight. So in here, if we see, we have divided them profit by weight. So here is this value. That is 1, 1.63, 1, 6, and 4.5, and 3. Now, if we see, now after dividing this by profit by weight, we can see over here is that summation of xi and wi. We can solve it, and we, by solving it, we can see that 1 multiplied by 2, 2 by 3. Just a second. Okay, so now we are taking the value of x1, x2, x3, x4, x5, x6, and x7 over here. So I'll be solving like this. So here, as we can see, the profit by weight 6 is the maximum over here. So the capacity of the bag was 15. So what I will do is that I will do 15 minus 6. So 15 minus the profit by weight over maximum over here is for 6. So the weight over here is weight for that object over here is 1. So I will do is 15 minus 1. That is 14. Now I will take 14 minus after 6 we have is 4.5 over here. So for this we have -14 minus 2 is 12. Now we will take 12 minus
Yeah, we can go ahead.
Okay. So after getting profit after dividing profit by weight, we are getting all this value over here. If we divide 10 by 2, it will be 5. Sorry. And this will be 1.6. This will be 3. 15 divided by 5, this will be 1, this will be 6 as it is, and this will be 4.5 and 3. So this is the value we have got for profit by weight. So now if we see over here, the maximum profit by weight is a 6 over here. So what we will do, and we also know the capacity of the bag. So the capacity of the bag was 15. So what I will do is 15 minus the profit by weight is 6. So its weight is 1 over here. So I will subtract 15 minus 1, then the value will be 14. Now after 6, the maximum value is 5 over here. So I will take 14 minus the corresponding weight of 5 over here is 2. So I will subtract 14 minus 2, which is 12 over here. Now again, I will take, similarly, now I will take for 12 after 5, the maximum value is 4.5. So I will subtract 12 from 12 minus 4, that is 8. And now after 4.5, the value over profit by weight over here is 3. So here also we are getting 3, here also we are getting 3. So we can take any corresponding weight. So I am taking over is 8 minus 5 is equal to 3, and 3 minus 1 is equal to 2. And similarly, after solving by this method only, at the end we are getting just so 8 minus 5 is 3, and then again 3 after this we are taking this weight, profit by weight. Then we are getting 3 minus 1 is equal to 2. And now over here, if we see, we have profit over here 5, but the capacity is not much. So we are going, we have left over here is only 2. So we cannot subtract 2 minus 5. So it will go in negative. So as we have already discussed in greedy method, we can divide the values over here. We can take in the form of fraction. So what we will do is that we will take only 2. We will take only 2 weights from this 3. So 1 is not included. So we are subtracting 2 minus 2, that is 0. So here, over here, we have seen that the last one which is left, that is x4, we are not including that in this case. So here the value of x1 is 1, and x2 is 2 by 3, and x3 is 1, and x4 is 0, x5 is 1, x6 is 1, and x7 is 1. So this is the value of xi. Now after getting the values of xi, we are solving it by taking summation of xi wi. So we are after solving this, we got the weight as 15. So it is equal to 15. So the constraint is solved over here, that the maximum weight should be less than equal to m. So it is 15. So it is satisfied. Now we want the maximum profit. So to get the maximum profit, we are going to solve the summation of xi pi. And after solving this, multiplying the values of xi with the profits, we are getting the total profit as 54.6. So this was the greedy method for solving knapsack problem. So the second method is when the items are indivisible, as I already discussed. If we are we have to put some things like fridge, mixer, we cannot divide them. So the items are indivisible. You either take an item or not. So in this case, we can take an item or we cannot take. So we are going to solve this method using dynamic programming. So 0-1 knapsack problem is suppose a thief A thief has a knapsack with maximum capacity of weight, that is W, and is set S containing with n items. So as we all know, each item I has some weight, that is Wi, and benefit value, that is also called as profit value, will be Vi. So all Wi, Vi, and capital W are integer values. So the problem over here is how to pack the knapsack to achieve the maximum total value of packed item. So our goal over here is, as we have already discussed the constraint, so we have to find xi such that for all xi that is equal to in the set 0 and 1, I will be for 1 to n, our summation of Wi xi should be less than equal to capital W, that is weight, and summation of xi Vi is should be maximum, that is profit should be maximum. So this is the example given over here, which we are going to use to solve the dynamic programming. So our items is from 1 to 7, and the benefits, or we can call it as profits, are given over here, and the weight is this. So we have the constraint that knapsack holds a maximum of 22 pounds. So our M over here is 22, and we have to fill it to get the maximum benefit. So using this method, brute force approach, so what we will do is we will solve this problem using straightforward forward algorithm. As we have as in dynamic problem, we have to take the combinations. So we have to check how many possible values are we will take the possible values over here. So since there are n items, then there will be 2 to the power n possible combination of the items. We will check for each combination over here. So that is why we have 2 to the power n possible combination of the items. And also as we go through all combination, we will find the one with the most total value and total weight less or equal to W, and the running time complexity of this will be 2 to the power n. So here this is a PIW is the maximum profit that can be obtained from item 1 to I for the knapsack with the size W, and in case 1 the thief is taking the item I. So this is the condition over here for taking the item I, and in case 2 when thief does not take any item I, then this will be the condition for that. So over here, the recursive formula we get is that P of IW will be P of I minus 1 comma W if our Wi is greater than W, and otherwise it will be maximum of Vi plus P of I minus 1 W minus WK and comma P of I minus 1 comma W. So the best way to get is that the total weight either contains I or I naught. So in first case, what we will check is Wi will be greater than W. So item I can't be the part of solution, since if it was, the total weight would be greater than W, which is unacceptable. So second case is Wi should be less than equal to W, then item I can be included in the solution and we can choose the greater value. So here, so okay, so this is the example over here. So we have items, weight, and their values over here. So here the item 1, 2, 3, 4 their corresponding weight and values over here. So we are going to solve this using a table. So we have arranged a table over here where this is BW, that is 0, 1, 2, 3, 4, 5, and these are the object over here. So here, as we can see, we have arranged this table. So at first, For zero wet, the values will remain zero as it is over here, and we are including zero object over here, so this table will also be zero over here. In this column, the values will be zero, and in this first row, the values will be zero. So now, in this first item over here, we are taking our, for the first item, the value is 12 over here. So we are, and its weight is 2. So for weight 2, we are going to put 12 over here. We will put the value of 12 over here, and this will be 0 as it is. So we cannot put any other value. So we are putting 12 over here, and for 3 and 4, it will remain 12 as it is. So in this case, if we have solved the first row, also we can use this formula, that is Pi comma W, that is maximum of Vi, plus Pi minus 1 comma W minus Wi, and Pi minus 1 comma W. So we will take the maximum values, and by using this formula, we are going to fill this table. So for P of 1 comma 2, that is so for P of this 1 is the row and 2 is the column. So for 1 comma 2, by using this formula, we are by using this particular formula, we are getting maximum of 12 plus 0 comma 0, which is 12. Similarly, for solving P of 1 comma 3, we will get maximum of 12 plus 0 comma 0 is 12. So this is how we will fill this column for row for the first one, and similarly for the second one, that is P of 2 comma 1, the value over here is 10. So, and the weight is 1. So for 1, we will put 10 over here, and for 2, we will solve like this. For 2 comma 1, the value is 10, and for 2 comma 2, the value is 12. This is how we are going to fill all this table using this particular formula over here. So after filling this table, we will get the values over here, and then we have to check the optimal solution over here. So in this case, we are going from the downward direction. So we will check the optimal values from the downward. So over here, if we see the 37 is the maximum over here. So for taking the values of xi, that is x1, x2, x3, and x4, the maximum value over here is 37. So we are going to include the fourth item over here. So if we check over here, 37 is only in the last row. It is not anywhere else. So for this, we are going to take fourth item. Now, if we go up, 21 is the highest. But as we can see over here, we have 22 is the high over here. If we go, sorry. So in this case, we are going to take 37. That is item number 4, and then we will go upward. Then we will take 22 as 22 over here. We have 22 also in this row, that is second row. So we will not take item number 3, but we will take item number 2. And as we go up, now we have the 12. So 12 is also not anywhere else. So we are going to take the item 1. So the items which we are going to include in the knapsack over here is item 1, item 2, and item 4. So we have started P of n comma W. So we when you go from left to up, from downwards to upward, the item I has been taken, and when you go straight up, item I has not been taken. So like this, if we are going in this way, the items are taken, and when we are going in straight way, the items are not taken. So finally, we have taken the item 1, 2, and 4 in our sack. So the optimal substructure was that we are taking the most valuable load that weight at most W pounds. And if we remove the item J from this load, the remaining load must be the most valuable load weighing W minus WJ. Then that can be taken from the remaining N minus 1 items. So this is the algorithm for the knapsack 01 knapsack algorithm. So at first we are taking the loop from W is equal to from 0 to capital W. So our initial will be we are initializing it with 0, and we are again taking for loop from I 0 to N. Our value P of I comma 0 will remain 0, and then we are going to take for W is equal to 0 to capital W weight. If our Wi is less than equal to W, then item can be the part of the solution. Then we are going to use this condition which we have formula which we have discussed above, or else what we will do is we will take the previous value only, that is P of I comma W, that is equal to P of I minus 1 comma W, or then else this is the value for Wi greater than W. So the conclusion was that dynamic programming is a useful technique for solving certain kinds of problems. So also when the solution can be recursively described in terms of partial solution, we can store this partial solution and reuse them. So I'm done.
Okay, fine. Are there any questions? Yes, you can go ahead.
Good morning to everyone. I'm going to talk about hash functions. So far we have seen some of the algorithms that deals with encryption and decryption, some confidential text. Of course, we have seen digital signature covered by Ankita, I think, and visual cryptography is some part is covered by Sir. But what if we need to convert our folder or some file, PDF file, text file into a secret code? So that's where the hashing functions come into picture. So the hash function h takes an input m and convert it into a hash code h of m is equal to y. This y is also called as message digest. Now we will try to see some conditions for hash function. So I have a hash generator software here. This is, you can download it from anywhere, and these are some standard hashing functions that are being used around. And if we generate hash, that is notepad.exe, that is the thing, we will see that it creates a hashing code, hash code of very large value. So now you observe that the size of this file is 0.17 MB. So if I change the, let us see, take something, this is my files, and if I generate hash, the size is 0.63 MB. But the size of length of hash function, the hash value, remains the same. So this is the hash length. So this is 20, this is 32. If I change anything, then this is the large size from the file I have, 0.63, but still the hash function, does something happen, sir? I'm here. Hello.
Yeah, you are there, but
Okay.
it is not moving actually. Yeah, I think. Yeah, go ahead. Are you moving
Okay.
slide?
No, I'm not moving slides.
Yeah,
Okay.
yeah, right.
So now again, if you observe that, let us look at this SHA 256. Uh, this is 32 hash length. And again, if I take some other size uh, file and generate hash, this is 3.37 MB. So this is very larger file, but still the hash length remains same. So this 32. So this is one thing that anything we have, any size file of any size we have, the hash length, if you are taking some particular hashing function, the length must remain same. Okay. And another thing is that we also want to have this hash very secure. I mean, our file very secure. So one thing is obvious that given any message digest, it should be nearly impossible to get our original file. So if we observe that any random file, if I see any here, if I write my name here as a text and generate hash, so see, it is very complicated things going on here. So this is the thing we should, if we have only message digest, that is hash value, we should not be able to get our original message. Now the second thing is,
Also, we can only see our slides.
okay. This is so whatever I was saying was, okay. I'll have to repeat. Okay. So can you see this now? Hash generator.
Yes.
Yeah.
Yes.
Okay. Oh, I'm extremely sorry. So I'll repeat. Okay. So this is the one file I have taken for size 3.37 MB. And these are some of the standard hash functions. You can download this software from anywhere. This is hash generator. And these are some standard hash function creating the hash value of my BSc marksheets.pdf file. Now, the point I wanted to make that if let us observe this SHA 256, this is the 32 length, hash length is 32, and the size of this file is 3.37 MB. And if I change the file, let us take this some another file, the size is 0.63 MB. But if you observe that 256 SHA 256, the length remains the same. So this is the one thing that any file of any size we take, a folder, a file, the hash value, the length of hash value should remain the same. So that is the one point I wanted to make. And another from this slide, there's one thing is obvious that if whatever we have our message, we need that secure. So if we have only the message digest or hash value, we should not be able to get back to our original file. So that's why I written Kaunil, and the hash value, as you can see, it's very big and complicated. So if we get only that, we should not be able to get this. But another thing we should make sure that if I change some alphabets in it, and let us first copy this code from this lm hash type and copy this in the notepad. And if I change, let us say E instead of that, or let me do something. So this is generate hash. I'll copy this hash. And if I change this E and see, observe that is copy, I'll copy this. Did that change? Yeah, it changed. And I'll have to make some different arrangements. So let us try my full name. Actually, it worked just before I saw, but let us try again. let me check some examples I have written down. Let me give me some time. Yeah, sorry for that. So yeah, this is the one thing. Let us try to. Can you see this hash generator? Hello.
Yes, yes, it is visible.
Okay. So let us see this text. I love you, Alice, and just copy the hash of this. And if I change this message a bit, let us remove this C and copy this hash. So this hash is same. So this method is not that good if we talk about it. The message is, if doing some bit changes in the message, we are able to get the same hash. So this is called as collision. So that is the one thing. And another thing is that if we have a hash function, a hash message digest, and so these are the observations. So given a length input of any size, that should be of the same length. And if given an input and a hash, then it is difficult to find another input which maps to same output. So given an input, a message digest, if you find inverse of that, I know what is the hash function. So we should not be able to get to some another file. So that's how the hash should be very good. And the one thing I've showed is the collision property. So this is the collision thing that hackers do. If they have a message digest and they know what is the original file meant to say, they change some bit in the fraud files to get to this hash. So as I changed, the message was "I love you, Alice," and I changed that C. I removed that C, but the hash was same. So message got changed. Yeah, of course, this was very small example, but with very big things like some agreements, there see digital signatures. These collisions are used by hackers. So we will see that when we talk about birthday attack problem. So now let us look at some limitations of our hash function. So our hash function takes input of any arbitrary size, as I said, and produces the input of same length, output of same length. That means there exist infinitely many inputs mapping to same hash code or digest. So just by changing some things, there is some limitations to number of hash codes. Like if we take 128 bit or say 64 bit hexadecimal codes, binary codes, anything, it has some limitations. The 2 64 codes will be there. But I am talking about any file of any size, and it maps to the same a different hash code. So when we say it is nearly impossible, or it is the solution is infeasible, that is, it is practically impossible if we have only message digest and we get to the some different file if we know the size. But theoretically it is possible to find many files of same hash code. So that's why the collision is the problem. Nowadays we find collisions for many old standard hash functions, as we have seen that lm function with the help of computer. And that's why for security, purpose, our length of our code must be at 128 bit minimum, or otherwise it is suggested, if it is not a security point of view, it is suggested that our code should be 256 bits. But again, 256 bit is again a large code. We need to calculate a lot. Computer must be able to do that. And to crack this binary 128 code bit, the hacker need to do 2 raised to 128 computations to crack the algorithm. But this is true actually. We'll see that in birthday attack problem, that hacker don't have to do these many calculations. They use some algorithm, they try to reduce it. So this is the thing. We have a file of X size mapped to hash code. We shouldn't, it should be impossible nearly to get some X plus epsilon size file mapping to same hash code. So that's what we are, that's all about the hash function, all the requirements it needs to be hashed, all the limitations of hash functions. So now we'll look at some, this is very popular attack. That attack, the word attack means that it is done by hacker on some files. But to understand this birthday attack, we need to understand the birthday paradox. So let us try to look at it. Now suppose we have 23 group of 23 people, and we are interested to find what is the probability that two people having the same birthday. Now there are total 365 birthdays, that is 365 days in a year, and if we look at it, there are too many days. So for a group of 23 people, 365 total birthdays, so intuitively we can think that probability is going to be very less for these many days. But if we calculate, we'll see that there is 50% chance that two people having the same birthday, a group of 23 with a group of 23 people. So we'll try to calculate the probability, and for that we will calculate, first we will calculate the probability that two people are having no people have the same birthday. Okay, so suppose that, I'll just write, suppose that first probability, the first person, we select first person and his birthday. So he has 365 many choices to select the birthday. So probability that first person having the birthday different from other, it is going to be 1. So that is actually 365. I'll just, so the first person having birthday as probability (365 by 365), that is 1. Now this, for the second person to have the birthday different from him, he has the choice of 364, right? So first thing is taken, already taken. So he has a choice, that is, so second person has 364 possible choices. That the probability that is not same is going to be 364 by 365, which is 1 minus 3 sorry, 1 minus 1 upon 365, right? Now again, the third person, for third person, it is going to be 363 upon 365, and so on till we get to the 23rd person. So this is going to be so that is the probability, so implies the probability of not having is product of so first thing is taken, so we will going to have a product of here, it is going to be the second percent, it is 1, third percent, it is 3 by the 2 by 365. So it is going to be I ranging from 1 to 22, that is R minus 1, 1 minus I 365. It should be 0. Okay, so if we calculate this, we will see that once we find the approximation for this, a better approximation for this, we will going to evaluate that. We'll find I have written some program, a basic program. We don't need that much. So going to be somewhere near 0.49 something. So this is the probability of not having the birthday, and then the probability implies the probability of having same birthdays by two people. Of course, there is for some two people, there's a negation. 1 minus 0.49 something, it is going to be 50.71, so on. So this is, we'll see how we get this. So there is a 50%, oh sorry, it's not 50 point, this is going to be 0.5071, so there is a 50% chance that two people having the same birthday. So for calculating this for very large n, it is very infeasible, not feasible. So that is the point we will try to see. So there here is n was 365. So that is very small if we try to look at the programs. But as I have said that there are 128 256 bits program to do calculations. So that's why let us try to explore or find a proper approximation for this. So for that, let us assume two functions, that is f of x is equal to natural log of 1 minus x plus x, and again g of x as another function, that is log of 1 minus x plus x plus x square. Okay. Now if you find its derivative, is going to be 1 upon 1 minus x plus 1, and if you find this derivative, this is going to be 1 upon 1 minus x, or this is going to be minus, sorry, plus 1 plus 2x. Okay, so we are why we are doing this, we are trying to find the nature of f of x and g of x. So if you plot this function, so here is the plot. Here is the plot of the function. So this is the f dash of x, the red one, and if you observe that f dash of x is it is f dash of x is less than 0 in the interval 0 to half, and g dash of x is greater than 0 in the interval 0 to half. So we will write this down. So this is f dash of x is less than or equal to 0 for interval 0 to x half, and this implies g dash of x is less than or equal, oh sorry, greater than or equal to 0 for 0 less than x less than half. Now if we look at f of sorry so sorry, if you look at f of 0, that is again log of 1, that is 0, and g of 0 is again 0. Now we know for the fact that if f dash of x is less than 0, then f is decreasing, and if f dash of x is greater than 0, then f is increasing. And f of 0 is equal to 0. So f of x, so we can say safely from here, we can say that f of x is less than or equal to less than 0 in the interval x to half for x in to half. This implies that log of 1 minus x is less than or equal to minus x. And again, g of x is greater than or equal to 0 for x in 0 comma half. This will imply that x minus x square minus x square is less than or equal to log of 1 minus x. So to put together, this will imply, so this is the important inequality we have got, that is minus x square is less than or equal to ln of 1 minus x, which is less than minus x. So this is some important. I'll just box it up. Again, and all these things in the interval function, in the interval 0 to half. Okay. So now let us try to find out the proper expression for what we are looking after. So as you can see that the product is like 1 upon 1 minus product of 1 minus I by n, right? This one here is nr, and total number of things. Okay, so yeah, oh, I'm so sorry, I have not talked about it. Okay, so now what we are trying to do here is we are trying to find a general case. So suppose we have n many objects, and r many people. That is same as r people having the 365 birthdays, and we are trying to find out again the same thing. 2 people having the same birthday. Instead of that, we are looking for a person selects same object. Okay, so with replacement, of course, so that many people can select same object. It is not without replacement. Okay, so now we'll let us substitute here in this inequality. We'll substitute some I or j by n. So it is going to be equal to let x be j by n. This will imply minus j by n minus j square by n square is less than or equal to limit, not limit, 1 minus j by n. This is less than or equal to minus j by n. Okay, and we will take a sum of both the sides from j going from 1 to r minus 1. So r, as I've shown in the example, this is r minus 1, that is this 22 here is r minus 1. So that's why we are taking sum over r minus 1, j by n minus j by n minus again sum of j going from 1 to r minus 1 j square by n square is less than or equal to sum of log of 1 minus j by n, that is less than or equal to sum of minus j by n. Okay, now we know that the sum what the sum is going to be of these quantities. So this quantity sum is going to be summation 1 upon minus 1 upon n r minus 1 into r by 2 minus 1 upon n square. This we also know that this is going to be r minus 1 r and 2r 2n plus 1. So n plus 1 2 minus 2, so minus 1 n into n plus 1 by 6. It is less than or equal to some log of 1 minus j by n is less than or equal to, again the same thing here. So now this doesn't help us. I mean, this is not proper. We are trying to find the proper approximation for this, but this is not going to help. So let us try to explore this. This quantity will try to go with this quantity here. We'll try to find some better inequality for this, because other thing is this part and this part is very similar. Oh, I've missed the 2 here. Okay. We'll try to find a approximation for this. So let us first simplify this one. So r sorry, r minus 1 into r to r minus 1 by 6 square minus r to r minus 1 by 6. This is going to be 2r cube minus r square minus 2r square plus r by 6. So this will imply, I'll write it here, r cube by 3, right, minus, or let us keep it that way, r minus 3r square by 6, right? So this is the thing we got. Now we know that r is again some number 1 2 3 4 so on. So r is going to be less than r square. Again, this is going to be less than or equal to 3r square. This would imply that r minus 3r square by 6 is less than 0, right? So this is some negative quantity. We can, if we remove that negative quantity from here, so this is going to be it's going to be I'll just write it down again, r minus 1 r 2r minus 1 by 6 is going to be greater than or equal to some r, this r cube by 3. So this thing we have, we are removing a negative quantity from it. So this is negative. So that's why we have this one. I'm sorry, this is not. This not writing. Okay. Let me reshare. So yeah, this is going to be less than r cube. So we are removing a negative quantity. So this will imply that the negation of that is going to be greater than that. So we will from that we will get this quality. I mean, for here, this here, green part here, we will substitute this inequality there in negative sense. So why don't we just uh, won't work. Anyways, let me write it down. Okay. Okay. So we will from that we will get that r minus r minus 1 r into r minus 1 by 2n minus r cube by 3n square less than or equal to that sum part j equal to r minus 1, right? Okay. Then 1 minus j by n is less than or equal to, again this was right, minus r minus r minus of r to r minus 1 by 2. So we get this inequality. Now let us take some define this lambda as r square by 2n. Okay, and we will assume that, or yeah, we will assume that lambda is less than or equal to n by 8. So that is the condition we require. That this implies that r is less than or equal to n by 2. So we are trying to be more precise with the calculation, that we are choosing r to be less than n by 2, the total number of people by 2. Okay. So now what we have here, yeah, so yeah, this is the natural log. If we take e to the power everywhere, so this is going to be pi of this. So I'll just write it down. So before writing down, I mean, this is very tedious for just writing. So I'll just try to simplify and then write. So let us try to simplify this quantity, this entire quantity. Okay. Our goal is to finally find the approximation in terms of some exponential value. So this quantity we will try to simplify. So this is what r into r minus 1, that is by 2n minus r cube by 3n square, right? So did I write minus? Minus, yeah. So we will what we will do is we will try to get this entire thing in terms of lambda. So let us try to do that. This is r into r minus 3 outside, of course, minus plus upon 2n, right? And this is minus r cube by 3n square. So this is going to be what? Minus lambda, right? So this is r square by 2n plus r by 2n minus r cube by 3n square. Right. So this will imply that I'm going here from here. So look at here, lambda minus lambda. Let's take square 4n square plus this is going to be in the square root minus, let us take this r square into 3 by 2. It is going to be r cube. This 3n we will take out. We'll take this n here. Trying to find something in terms of lambda. So that is going to be minus lambda plus 1 upon root 2n root lambda, right? So 2n south r square by 2n. So root lambda minus, let us do this, 2 raised to 3 by 2 upon 3 r square upon 2 n. Here n, this n is here, so this is this n raised to 3 by 2. Now here we have what we had is n, and we are writing this in 3 raised to n, 3 by 2. So we need to add something to 3 by 2 to get this to 1. So of course we all 3 by 2 minus half is going to be 1. So there is going to be root n term left. Oh, sorry, minus root n term left, which is going to n raised to minus 1 by 2. Right? So what we have is minus lambda plus 1 upon 2 root n root lambda minus 2 raised to 3 by 2 up to 3n lambda to the power 3 by 2 into root n. So root n is going to be here. We're left with root n. I just directly write down. Okay. Now if we take common minus lambda, we take common root n plus 1 upon root n into some square root of lambda by 2 minus 2 raised to 3 by 2, 3 root n lambda to the power 3 by 2. So we will call this as some a1. A1. Okay. Now this part is not that difficult. So let's see. This is that require as much. So that is fine. R minus 1 up to n. Right? This was the part. So that is just minus r square by 2n minus r, sorry, plus r by 2n. So this is just a part, this part of this. So this part, first part of this minus lambda plus 1 upon the root n into root lambda by 2. Right. So we will call this A2 as A2. So what we have now is a nice approximation for uh, this. So if we take the exponential of this quantity here, exponential of this quantity here, it is going to be e raised to this. So finally we will get e raised to minus lambda into e raised to a1 by a1 by root n less than or equal to pi of j going forward to r minus 1, no, 0, 1 minus j by n less than or equal to e raised to minus lambda e raised to a2 by the root n. Now, if we take limit on both the sides, what we will get is it is going to be sandwich between these two, and this term here, this term here, and this term here is going to tend to 1 as n tends to infinity. So what we will get is a nice approximation for our a person for not choosing the same object. So j r minus 1 minus j n is approximately equal to e raised to minus lambda. And for two people, or any two people, or sorry, not any two, for some two people having same birthday, it is going to be 1 minus j going forward to r minus 1, approximately equal to 1 minus e raised to minus lambda. So instead of calculating the thing, this lambda we know, where lambda is r square by 2. So instead of calculate for what did I write? Oh, I did not write inside the pi of j 1 to r minus 1 minus j by n 1 minus that is going to be this. So we got a nice approximation. We'll try to see it in the program, but before that I forgot one thing that I'll like to explain. This is very applicable whenever you go to some website. So what is the point of all these files and data security? What is it used? So many times you might have observed that when you go to some website, this is not a nice website. This is a website to download pirated films. So when you go to some website like this and you click on anywhere in the on the screen, it will redirect you to some another page. This happens many times with many websites. That is not important. This is going to redirect you. So that is the point here. Some transparent layer of advertisement or something is going on. If you trust your website, there's no problem with that. But if you don't trust a website, so what we have is I'm going to show you one thing that is this is very popular website called as Pirate Bay, and of course this website is to download pirated contents. So I'm not going to do anything from here today, but what it gives you whenever you download any file, we never observed all these things, but there is something like, first of all, can you see this screen now? Hello?
Yes, we can see, but your voice is little breaking. Yeah.
Okay.
So now, right now, we are showing
Sorry.
fundamentals of electric machines, a Premiere with MATLAB, right?
Yeah. This is one. Let me go. Someone might be using Wi-Fi, so let me ask them to shut it off. So give me a second. कोणाचं वायफाय चालू आहे का? कोणाचं वाय चालू आहे का? माझं अडकतंय तिकडे.
Stop, back off.
You can proceed actually. Yeah.
Yeah. So sorry, sir.
Hmm.
I just turned off all the other devices for Wi-Fi. Okay. Now, yeah. So as you can see here, some info about hash is given. So for download any file from this, there is one thing called a magnet link. It provides get this torrent by magnet, and this magnet link contains info about the hash. So when you know whether there is some transparent layer or not. This website might be hacked. So and anyways, this torrent magnet link, there is some transparent thing going on where same name file, but some virus or anything a hacker wants to corrupt your system. So how do we make sure that whatever we are downloading from website, of course, this website is not a very proper way to download anything. So uploader may be a hacker or something. But what is uploader is making sure that whatever he is giving, a person should be able to download that. There is some security sign, of course, but okay. I'll just copy this magnet link, just paste it here. Okay, so this is very big magnet link. Oh, this is, oh, anyways, you can see it here that you can also, let me go and let us copy paste, then we will see. Okay. So this is the onion site. That's why the link is very big. The onion site is, Tor is very secure thing uh, going on these days. And this is this is the place where you find all fraudulent activities, hackers and all. Anyways, this is not the point. This is I have copied, and this thing given here. I'll copy this. Yeah, so you can verify that whatever he is giving, I am downloading the same file. And of course, after you download it, you can again take anything. He'll give you some folder, and in that folder there will be your file, the information about uploader, some in setup info and all. If you take any file from that folder and uh, upload that in the hash generator, so here file hash generator, you will see some match in some thing. I think is this, I have checked with something, I cannot show you now, but it uses MD4 method. This is also very standard. These days many people use SH256. So yeah, that is one thing I wanted to talk about hash. So this is the whole point of hash. We need to be secure while what we download, and uploader is making sure that whatever you download, you verify it. So you verify. Every website don't give you this, but some of them does. Okay. Yeah. Yeah. So what is the point of all this birthday attack and all? So what we are trying to say is that if we have a hash function, hash digest, message digest, we will try to, I mean, the hacker will try to find something else having the same hash code, which has a fraud thing. So for example, suppose Alice and Bob got married and they signed a prenuptial agreement before that. So that agreement contains, after if they get separated anytime, they will share their things 50%, 50%. They'll sign the agreement and they'll make a hash code of it. And then Alice go to Eve and tell him that this is the hash code. This is another file. I want 100% of the property. So Eve will take the file. Eve will create one agreement which says that this is the thing. After they get separated, Alice will get 100% of that. He'll create a hash code, and that hash code is going to be different. So he will change some maybe commas, some alphabets, some texture, some way of font is written, some images. As I have shown that hash code, the text I love you Alice and I removed C is the same thing. So he'll try to make that and compute hash each time. Once he gets same hash, they get separated. Alice is going to have all of that. So here she will say that this agreement, take the hash code, it is causing collision. This is the agreement. It says that Alice will get 100%. So that is the huge problem these days. So that's why collision is the thing. If we have, let us try to explore one important property of this. So if you have, if I have a file, let us say this is my file, and if I convert it into a hash code, that is h of m, this is my message, this is my hash code, and some okay, so I'll make a group S of these messages. So let S be the group of some digital signatures, maybe let us say some agreements, legit agreements, legit and authentic agreements. So we will try to find the hash h of s for all s belongs to s, and let T be the fraud. So let T be the group of fraud docs agreements. Let us say let us say cardinality of S is 30. And we will try to find h of t for all t in t. And now what we need to do is that we have a 30 agreements which are legit. We have a group of fraud agreements. Of course, the cardinality is same as S. Cardinality of T is same as S. And to find some collision, to find some probability that some document in this S is same as the document in T, that is, we are interested to find the birthday attack problem gives you probability that there exists some x1 in S and x2 in S T with such that h of x1 is same as h of x2. So that's how we try to find the collisions. And how do we choose this n? So there is one way we can choose. I mean, if you want a good probability, sorry, n is fixed, n we already know. How do we choose this r? So how many codes do you need to take to make some collisions? if you have a group of R codes and there is n many codes around, how do you choose some, sorry, if you have one code and there are n many codes around, how do you choose a group of R with the codes you want to find collision? How do you choose this R? So one way, as we have seen this approximation just now, uh, this e raised to so what is that? The probability of having a match is what we have seen is 1 minus e raised to minus lambda, right? So now if we choose this lambda as let us say log of 2, what is it going to be? If it is log of 2, then this probability is going to be equal to 1 minus e raised to minus half, no, e raised to just half. I'm sorry. So this is going to be somewhere near to 50%. Okay. And what does this mean? That's lambda is r square by 2n log of 2. This will imply that r is approximately, you can calculate it, r is approximately 2.77 something. So what is this saying is that if we have, I'll just write a conclusion here. Conclusion. If we have approximately root n many people, then we have 50% probability of match, right? And if you increase this number, let as some 2 root n, 10 root n, it is going to increase the chance. It is going to increases the chance of match. Okay. So instead of taking some multiple of n, we are taking multiple of root n. But this is all fine. I mean, if we take two groups, we will find some collision. In some, we will find collision with probability 0.5, that is 50% of the chance, 90% of the 90%, 91% of the chance. That is all fine. But what we are interested to do is some specific phi that we need to collide with some other thing. But that is going to be very tedious task, right? So this is fine. But if you want to find some thing like, let us say, well, I'll show you in the program. So main thing is that we need to find some collision to our code, and the good way, a better way to do is make a two group with that and try to find if we are getting a match to our code with doing several calculations. Okay, if I want to find that something that is if my birthday, if I am in the group of 23 people, my birthday is matching to someone else's birthday. So if say my birthday is, so it is going to be probability of not having same birthday as me. So I have one birthday any birthday selected, and let us see that what is it going to be. So second person should not have a birthday same as me. So 1 upon 1 by 365. Again, the third person should not have birthday same as me, 365, right? He can have birthday same as second person, but he should not have birthday same as me. Again, this is going to be 365 and so on. So it is going to be equal to, in a group of 23 people, 65 by 22, right? So that is again 364 by 365 by 22, and it is going to be very large quantity. Then let us, I think this is some 0.91. I'm not very sure of that. You can calculate it, not very difficult, but it is going to be. And then the probability of having same detail as me is going to be 1 minus 0.91. That is going to be 0.01 something. Wow. So it is very, very low probability that it will happen. Right. Right. This is 0.01 something. So this is very, very less probability. There is a 10% probability the same person. So that's why we make a two group. We have good documents, we have fraud documents, and then we try to collide. So now a specific task won't help us. If we have a good documents, we'll try to find collision and then maybe blackmail the person having the agreement with him, proper agreement with him. So that is the thing. This is the random selection. Okay. So that is for that I have written a small program. So yeah. So here is the thing. So you see 23 people having so this is not there, 0.006. I'll just take a note of this. 0.006. Anyways, whatever it is, 0.006 it is. So this is very less, right? This is near to 6% chance. So this is the program for birthday attack. Now what we have here is 365 days, 23 random person. Oh no, this is not correct. Sorry. I wrote, yeah, I wrote first some program, then define the function. That's why this happened. Okay. So they see 65 with this. So our birthday, there's 50%, 51, 72% chance that there is a match, and with approximation, there is 51 or something. Right. And this is what probability of having say having same birthday as you. So this is 0.6. If I change this number, so if I change this to 30, let us say 30 people. You see the probability is far better, 70%. And again, this is again increasing, but there is not going to be any difference. Let's say 43, I think that is the number you get the proper. See, 94% of probability that you will have a same per day as other person. So this is the thing. If we, that's why we use this. So let us say we have 2 to the power, let's say 128. So 128 bit program, just that. Syntax. Okay. And I'll take the square root of n. Of n. Let us not take just square, just take 3 star square. And this is not going to work. This is not Sage Maths. Okay. Yep, this is 128 bit program. I'm trying to find the birthday Oh, yeah. Okay. Now if this range needs integer value, so what was that to make it into a function? This, does someone remember the syntax for that? Kanak, maybe? Do you? I'll need to approximate this into an integer, that square root of n. What do we do? Does anyone remember that?
Use round.
Yeah, round. Yeah, but round also. Okay, let's see. This is the syntax, right?
Just round should go. I don't think it takes one.
Just round. Okay. Yeah, see, 128-bit, it is taking a lot of time to calculate this. So that program, my processor isn't efficient for this. I should have taken 64 or something. So that's the point. If we have even, of course, there are many nice processing computers are there these days, which you can calculate the thing. So yeah, that was my point. Of course, I should have taken, if I close this, stop this. If I take, maybe let us take which my processor can handle. Yeah. So see, if I take 32-bit program and 3 into square root of this, so there is a 98% chance that it is going to find the same hash function, hash code with the probability 98. So this is a good thing for a 32 bit. If I only take square root, it is going to be very less. See, it is just 39 or something. This may not be possible, right? So yeah, this was all about the birthday attack problem and hash functions, applications of them, and how to find collisions. I mean, not how to find collisions. So the probability, the word attack problem. So yeah, this much. Thank you for listening.
Okay, are there any questions?